On July 28, 1976, at Edwards Air Force Base in California, Captain Eldon Dewars pushed his throttles forward and felt the aircraft beneath him begin to shake. The SR-71 Blackbird was accelerating through Mach 3, and the external skin temperature was climbing past 600 degrees Fahrenheit. Somewhere behind him, Major George Morgan monitored the instruments as the speed climbed higher. Mach 3.1, Mach 3.2. The Mojave Desert slid beneath them at more than 36 miles per minute. At that velocity, they covered the length of a football field in less than 6/100ths of a second. At Mach 3.32, they crossed the timing gates at 2,193 miles per hour, faster than any air-breathing manned aircraft had ever flown. Faster than any has flown since. But inside that cockpit, speed was not what Dewars felt most acutely. It was the heat. The windshield just inches from his face had reached 600 degrees on its outer surface. 2.5 feet from where he sat, the glass was hot enough to bake bread. The leading edges of the wings were glowing past 1,000 degrees, approaching the temperature of molten aluminum. Engine cowlings reached 1,200 degrees. The entire airframe had physically expanded by several inches. The titanium panels that had leaked fuel on the ground now sealed tight by thermal growth. The aircraft was not merely flying, it was transforming. It was becoming something different at altitude than it had been on the tarmac. This is the story of the fastest airplane ever built, an aircraft constructed from metal secretly purchased from America's greatest enemy, flown by pilots in spacesuits at the edge of the atmosphere, shot at by thousands of missiles and never hit. This is the story of how engineers solved problems that did not have solutions, invented materials that did not exist, and built a machine that still holds records half a century later. This is the SR-71 Blackbird, the aircraft that flew so fast its skin glowed red. The airplane that would become the Blackbird was born from catastrophe. On May 1, 1960, Soviet May Day, CIA pilot Francis Gary Powers departed Peshawar Air Base in Pakistan aboard a U-2 spy plane, designated Article 360. His mission, codenamed Grand Slam, was the most ambitious American overflight ever attempted, a 3,800-mile route with 2,900 miles crossing Soviet airspace from Pakistan to Bodo, Norway, photographing missile sites at Sverdlovsk and Plesetsk along the way. Powers carried a silver dollar coin containing a saxitoxin suicide needle, which he was not required to use but could choose to employ if captured. The flight was scheduled just 15 days before a summit between President Eisenhower and Soviet Premier Khrushchev, where they were set to discuss arms control and the future of Europe. The mission had already been delayed. Twice. Eisenhower personally approved every Soviet overflight, sometimes altering flight paths with a pencil on the maps brought to his desk. He had approved Grand Slam reluctantly, knowing the summit was close. The weather window was narrow. Powers took off into a cloudless morning sky. Near Sverdlovsk in the Ural Mountains, the Soviet air defense network went to full alert. Radar operators tracked the black silhouette crawling across their screens at 70,000 feet. MiG-19 fighters scrambled but could not reach that altitude. Soviet air defenses launched a barrage of SA-2 surface-to-air missiles, NATO designation guideline. Up to 14 missiles streaked skyward in a salvo. Soviet records suggest that one MiG pilot attempting an intercept was accidentally struck down by friendly missile fire. None of the missiles scored a direct hit on Powers, but one detonated close enough behind his aircraft that the shockwave and shrapnel destroyed his horizontal stabilizer. At 70,500 feet, with no stable flight surfaces, the U-2 tumbled out of control and broke apart. Powers could not reach his ejection seat because centrifugal forces pinned him against the canopy. He manually released the canopy, fought against the spinning forces, severed his oxygen hose, and pulled himself from the disintegrating cockpit. He free fell for nearly a minute until his parachute opened automatically at 15,000 feet. He did not use the suicide needle. Soviet collective farm workers and KGB agents captured him upon landing in a field near Sverdlovsk. The Eisenhower administration initially believed Powers was dead. The aircraft had disintegrated at altitude, and no communication had been received. NASA issued a cover story on May 5th, claiming a weather research how SR-71 Blackbird flew so fast, its skin glowed red titanium at Mach 3.2. On July 28, 1976, at Edwards Air Force Base in California, Captain Eldon Jers pushed his throttles forward and felt the aircraft beneath him begin to shake. The SR-71 Blackbird was accelerating through Mach 3, and the external skin temperature was climbing past 600 degrees Fahrenheit. Somewhere behind him, Major George Morgan monitored the instruments as the speed climbed higher. Mach 3.1, Mach 3.2. The Mojave Desert slid beneath them at more than 36 miles per minute. At that velocity, they covered the length of a football field in less than 6/100ths of a second. At Mach 3.32, they crossed the timing gates at 2,193 miles per hour, faster than any air-breathing manned aircraft had ever flown. Faster than any has flown since. But inside that cockpit, speed was not what Joas felt most acutely. It was the heat. The windshield just inches from his face had reached 600 degrees on its outer surface. 2.5 feet from where he sat, the glass was hot enough to bake bread. The leading edges of the wings were glowing past 1,000 degrees, approaching the temperature of molten aluminum. Engine cowlings reached 1,200 degrees. The entire airframe had physically expanded by several inches. The titanium panels that had leaked fuel on the ground now sealed tight by thermal growth. The aircraft was not merely flying, it was transforming. It was becoming something different at altitude than it had been on the tarmac. This is the story of the fastest airplane ever built, an aircraft constructed from metal secretly purchased from America's greatest enemy, flown by pilots in spacesuits at the edge of the atmosphere, shot at by thousands of missiles and never hit. This is the story of how engineers solved problems that did not have solutions, invented materials that did not exist, and built a machine that still holds records half a century later. This is the SR-71 Blackbird, the aircraft that flew so fast its skin glowed red. The airplane that would become the Blackbird was born from catastrophe. On May 1st, 1960, Soviet May Day, CIA pilot Francis Gary Powers departed Peshawar Air Base in Pakistan aboard a U-2 spy plane designated Article 360. His mission, codenamed Grand Slam, was the most ambitious American overflight ever attempted, a 3,800-mile route with 2,900 miles crossing Soviet airspace from Pakistan to Bodo, Norway, photographing missile sites at Sverdlovsk and Plesetsk along the way. Powers carried a silver dollar coin containing a saxitoxin suicide needle, which he was not required to use, but could choose to employ if captured. The flight was scheduled just 15 days before a summit between President Eisenhower and Soviet Premier Khrushchev, where they were set to discuss arms control and the future of Europe. The mission had already been delayed. Twice, Eisenhower personally approved every Soviet overflight, sometimes altering flight paths with a pencil on the maps brought to his desk. He had approved Grand Slam reluctantly, knowing the summit was close. The weather window was narrow. Powers took off into a cloudless morning sky. Near Sverdlovsk in the Ural Mountains, the Soviet air defense network went to full alert. Radar operators tracked the black silhouette crawling across their screens at 70,000 feet. MiG-19 fighters scrambled but could not reach that altitude. Soviet air defenses launched a barrage of SA-2 surface-to-air missiles, NATO designation guideline. Up to 14 missiles streaked skyward in a salvo. Soviet records suggest that one MiG pilot attempting an intercept was accidentally struck down by friendly missile fire. None of the missiles scored a direct hit on Powers, but one detonated close enough behind his aircraft that the shockwave and shrapnel destroyed his horizontal stabilizer. At 70,500 feet, with no stable flight surfaces, the U-2 tumbled out of control and broke apart. Powers could not reach his ejection seat because centrifugal forces pinned him against the canopy. He manually released the canopy, fought against the spinning forces, severed his oxygen hose, and pulled himself from the disintegrating cockpit. He free fell for nearly a minute, until his parachute opened automatically at 15,000 feet. He did not use the suicide needle. Soviet collective farm workers and KGB agents captured him upon landing in a field near Sverdlovsk. The Eisenhower administration initially believed Powers was dead. The aircraft had disintegrated at altitude, and no communication had been received. NASA issued a cover story on May 5th claiming a weather research aircraft had gone missing north of Turkey. fabricating elaborate details about oxygen system difficulties causing the pilot to drift unconscious over Soviet territory. 2 days later, Khrushchev revealed the devastating truth in a speech to the Supreme Soviet. Powers was alive, had confessed, and the Soviets had recovered his surveillance cameras, 70 pounds of exposed film showing Soviet military installations and the wreckage of the aircraft itself. They even had the suicide needle. Eisenhower was humiliated. He considered lying, then chose to admit the truth. The Paris summit collapsed within a week. The planned arms control discussions never happened. Powers was held at Lubyanka prison in Moscow for 107 days, undergoing intensive interrogation for more than 2 months. His trial lasted 3 days in August 1960. He was sentenced to 10 years, 3 in prison and 7 in a labor camp. He served less than 2 years before being exchanged on February 10, 1962, for Soviet spy Rudolf Abel on the Glienicke Bridge in Berlin, a span that would become known as the Bridge of Spies. The shootdown proved what CIA leadership had feared since 1956. Altitude alone could no longer protect American reconnaissance aircraft. The SA-2 had changed the calculus permanently. Powers himself later reflected on what went wrong. The U-2 had flown too high to be touched for 4 years. Then suddenly, it was not. America needed something that could not simply fly high. It needed something that could outrun anything the Soviets could throw at it. The search for a U-2 successor had actually begun before Powers was shot down. Richard Bissell, the CIA officer who had overseen the U-2 program, understood better than anyone how fragile the margin of safety had become. As early as August 1956, he estimated the U-2 had perhaps 6 months of safe overflight time before Soviet defenses caught up. He was wrong about the timing, but right about the threat. In late 1957, even as U-2 missions continued, the CIA approached Clarence Leonard Johnson at Lockheed's secretive Skunk Works division in Burbank, California. Kelly Johnson was already a legend in American aviation. Born February 27, 1910, in Ishpeming, Michigan, he had risen from poverty to become the most innovative aircraft designer of his generation. He had played a leading role in designing over 40 aircraft, including the P-38 Lightning that dominated Pacific air combat in World War II, the P-80 Shooting Star that became America's first operational jet fighter, and the U-2 itself. He ran his Skunk Works operation by 14 strict rules, emphasizing small teams, minimal paperwork, direct communication with customers, and absolute autonomy from corporate bureaucracy. He lived by the motto, be quick, be quiet, and be on time. His design philosophy centered on the principle of keeping things simple, though the airplane he was about to build would be anything but. The CIA formed an advisory committee under Edwin Land, the brilliant physicist who had founded Polaroid and invented instant photography. Land had been instrumental in pushing the U-2 into existence, and now he chaired the scientific advisory panel that would evaluate competing designs under Project Gusto. On July 23, 1958, Johnson presented his first concept to the committee, a design capable of cruising at Mach 3. Convair, the aerospace giant, countered with its own proposals, including an exotic concept called Fish that would be launched from a modified B-58 bomber. Over the following months, Johnson's team drafted 11 successive designs, designated A1 through A12, each refining the aerodynamic concept. Convair eventually proposed a completely redesigned delta-wing aircraft called Kingfish. On August 20, 1959, both firms presented their final proposals in a tense competition. Johnson's A12 won on every metric that mattered. Longer range, higher altitude, and lower cost at approximately $8 million per unit versus Convair's $10 million. Equally important was Lockheed's track record. The U-2 had been delivered on time and under budget. On January 26, 1960, just 3 months before Powers was shot down, the CIA ordered 12 A-12 aircraft under a program designated Project Oxcart. The codename had been selected randomly from a classified list, and Johnson reportedly found it amusing that one of the slowest forms of transportation had been assigned to one of the fastest aircraft ever conceived. Development moved at extraordinary speed. Even by Skunk Works standards, the team faced problems that had never been solved. No aircraft had ever cruised continuously at Mach 3. No material had ever been manufactured in these quantities that could withstand such temperatures. No engine had ever been designed to operate at such extreme conditions for hours at a time. Johnson's engineers worked around the clock, inventing solutions as they went. The A-12 first flew on April 26, 1962, piloted by Lockheed test pilot Louis Schulk at the secret facility at Groom Lake, Nevada, the site that would later become known as Area 51. The aircraft broke Mach 1 just 8 days later and reached Mach 3 by July 1963. But the Air Force wanted its own variant, one with a second cockpit for a reconnaissance systems officer who would operate the sensor systems while the pilot flew, and the ability to carry more sophisticated sensors and cameras. This became the SR-71, about 6 feet longer and 15,000 pounds heavier than the A-12, with more prominent nose and body chines that housed additional fuel and sensor equipment. The designation itself emerged from Air Force internal deliberations. When Lyndon Johnson publicly revealed the aircraft's existence on July 24, 1964, the Air Force had already changed the designation from RS-71 to SR-71, placing strategic reconnaissance ahead of the number in the naming convention. The first SR-71 flew on December 22, 1964, piloted by Lockheed test pilot Robert Gilliland at Plant 42 in Palmdale, California. He took the aircraft to Mach 1.5 at 50,000 feet, and later described the maiden flight as relatively uneventful, just one emergency, a canopy unsafe light at Mach 1.2. The engineering challenges of sustained Mach 3 flight touched every system on the aircraft. At those speeds, aerodynamic friction heated the external skin well above 600 degrees Fahrenheit, temperatures at which conventional aluminum softens and loses structural integrity. Steel was far too heavy. Only one material offered the necessary combination of strength, lightweight, and heat resistance. Titanium. The A-12 and SR-71 were constructed from 93% titanium by structural weight. The primary alloy was beta B120 VCA, containing 13% vanadium, 11% chromium, and 3% aluminum. It was the only metal that could do the job. The problem was sourcing it. The United States domestic supplier, Titanium Metals Corporation, had only limited reserves. The raw material, rutile ore, existed in very few places on Earth. In the late 1950s and 1960s, the world's primary source and leading exporter of titanium was the Soviet Union. The CIA conducted what Ben Rich later described as a worldwide search for the metal. Knowing the Soviets would never knowingly sell titanium to build American spy planes, the agency established an elaborate covert procurement network of shell companies, dummy corporations, and third-party intermediaries operating through countries around the world. Titanium was purchased under fabricated purposes and routed circuitously to the United States. Rich himself put it most memorably in his memoir. The CIA conducted a worldwide search, and using third parties and dummy companies, managed to unobtrusively purchase the base metal from one of the world's leading exporters, the Soviet Union. The Russians never had an inkling of how they were actually contributing to the creation of the airplane being rushed into construction to spy on their homeland. Even after the raw material arrived at Burbank, working with titanium was extraordinarily difficult. Nothing in the aerospace industry's experience had prepared Lockheed's machinists for this metal. The alloy shattered like glass if mishandled. Conventional cadmium-plated steel tools embrittled titanium on contact, forcing Lockheed to design entirely new tools from scratch, using different materials. Chlorine in ordinary Burbank tap water corroded welded titanium joints, a problem that took months to diagnose. The solution required distilled water for all washing and cleaning operations. Even human fingerprints could weaken welds by leaving trace acids on the surface. Early drill bits lasted only 17 holes before becoming useless and being discarded. Spot welds that worked perfectly on other metals cracked titanium. Bolts torqued to standard specifications fractured the panels they were meant to fasten. Initial rejection rates were staggering. Up to 80% of delivered titanium batches were rejected due to contamination or manufacturing defects. The learning curve was brutal. Workers joked that they were building airplanes from a material that did not want to be formed into airplanes. Summer months brought new problems. Shop floor temperatures in the Burbank facility sometimes exceeded 100 degrees Fahrenheit, causing titanium sheets to warp before they could be machined. Lockheed eventually installed air conditioning in the titanium fabrication areas, a luxury in the early 1960s, not for worker comfort but because the metal demanded it. Over 20 years of production, more than 13 million titanium parts were manufactured for the Blackbird family. By the end of the program, Lockheed's machinists had become the world's foremost experts in titanium fabrication, a capability that would prove invaluable for later projects, including the F-22 Raptor. Johnson noted with satisfaction that the cost of one particular titanium bolt was eventually reduced from $15 to 25 cents during the production run. That single statistic captured the learning curve of an entire industry. The thermal environment the SR-71 operated in was unlike anything aviation had encountered. Skin temperatures varied dramatically across the airframe. The average overall skin temperature reached approximately 600 degrees Fahrenheit. Leading edges of the wings exceeded 1,000 degrees. Engine cowlings reached 1,200 degrees. The windshield exterior reached 600 to 620 degrees, hot enough that pilots used the cockpit glass to warm their meals during long missions. The interior surface of the windshield still reached 250 degrees, despite 1¼ inch thick quartz glass fused ultrasonically to the titanium frame. The aircraft's distinctive black paint served a dual purpose. Containing tiny spheres of carbonyl iron ferrite for radar absorption, it also served a thermal function. By the principle of blackbody radiation, the high emissivity coating radiated heat more efficiently, reducing skin temperature by 35 to 50 degrees compared to bare metal. The paint absorbed radar energy while simultaneously helping the aircraft shed the heat that threatened to destroy it. Thermal expansion transformed the aircraft's dimensions in flight. The airframe grew 3 to 4 inches in overall length during sustained Mach 3 cruise, with individual expansion joints accommodating 1 to 2 inches each. Major sections of the inboard wing skin were deliberately corrugated rather than smooth, allowing the skin to expand both vertically and horizontally without splitting. Aerodynamicists initially objected, calling it a Mach 3 variant of the Ford trimotor. Testing revealed an unexpected benefit. Titanium actually grew stronger from the repeated heat treatment it received during flight cycles. The fuselage panels themselves were a calculated compromise. They were deliberately manufactured loose, fastened with oblong holes that permitted movement during thermal expansion. At ambient temperature on the ground, gaps between panels allowed JP-7 fuel to seep through. Ground crews joked that you could tell an SR-71 was ready to fly when the fuel puddle stopped growing. At Mach 3.2, thermal expansion closed every gap perfectly. The aircraft that leaked like a sieve on the tarmac became airtight in the sky. The J-58 engine stands as perhaps the most remarkable power plant ever fitted to a manned aircraft. Designated JT-11D20 by manufacturer Pratt & Whitney, each of the two engines produced 34,000 pounds of thrust with afterburner. But what made them unique was their ability to function as two different types of engine simultaneously. Below Mach 2, the J-58 operated as a conventional afterburning turbojet. Above Mach 2.2, bypass valves bled air from the fourth compressor stage and routed it through 6 prominent external tubes around the combustor and turbine directly into the afterburner inlet. This system effectively transformed the engine into a turbo ramjet. At Mach 3.2 cruise, the engine approximated a pure ramjet. The thrust distribution tells a remarkable story. At full speed, only 17.6% of total propulsive force came from the engine core itself. The inlet produced 54% of total thrust, and the ejector nozzle contributed over 28%. The inlet's axisymmetric conical spike, which retracted rearward up to 26 inches to position shock waves optimally, was arguably more important than the turbo machinery behind it. The most feared in-flight emergency was an inlet unstart. This occurred when the carefully managed shock wave was expelled from the inlet, instantly killing thrust on one side. The resulting asymmetric force produced violent yaw that could slam a pilot's helmet against the canopy. Pilot Ed Yielding described it bluntly. You would be flying along and all of a sudden, boom. You would get a sudden yaw on the aeroplane because you would lose about 80% of the thrust on that engine. The fuel system was equally unconventional. Standard jet fuel would have ignited spontaneously at the temperatures inside the SR-71's tanks. Pratt & Whitney chemist Clarence Eichmann developed JP-7, a special kerosene blend with no more than 5% total aromatics, almost no sulfur or impurities, and a flash point of 140 degrees Fahrenheit. It was so stable that a lit match dropped on a puddle of it would simply extinguish. JP-7 cost 3 times as much as standard airline jet fuel and served double duty as the aircraft's primary coolant. It circulated through heat exchangers to absorb heat from engine oil, hydraulics, cockpit avionics, and environmental systems, before finally being burned in the engines. The fuel that cooled the aircraft was then consumed to propel it. But JP-7's extraordinary stability created its own problem. It was nearly impossible to ignite. The SR-71 used triethylborane, a pyrophoric chemical that explodes on contact with air at temperatures as low as -4 degrees Fahrenheit, producing a characteristic green flash. Each engine carried a sealed tank containing 600 cubic centimeters of triethylborane, enough for exactly 16 metered shots for engine starts and afterburner lights. Pilots tracked remaining shots on counters mounted on the throttle quadrant. When the chemical ran out, there were no more restarts. Total fuel capacity was 80,250 pounds, approximately 12,200 gallons, consumed at a rate of 36,000 to 44,000 pounds per hour. The aircraft was intentionally launched with reduced fuel loads and topped off immediately after takeoff by specially modified KC-135Q tankers carrying dedicated JP-7 fuel systems. Flying the SR-71 was less like piloting a conventional aircraft and more like commanding a spacecraft that happened to take off from a runway. The cockpit environment at 80,000 feet demanded equipment borrowed directly from the space program. Crews wore full pressure suits manufactured by the David Clark Company, the same firm that built suits for the Gemini program, and later the Space Shuttle. The final operational suit cost $120,000 and weighed 35 to 50 pounds. It consisted of 6 layers, an outer Nomex shell, mesh netting to prevent bladder overinflation, a rubber bladder pressurized at 3 pounds per square inch, a comfort liner, and insulated underwear. The fiberglass helmet featured anti-fog filaments and a port through which pilots could consume tube food during flights that sometimes exceeded 10 hours. The suits were not optional accessories. At the SR-71's operating altitude, the atmospheric pressure is so low that it crosses Armstrong's line at approximately 63,000 feet, the boundary where exposed body fluids begin to vaporize without external heat. At 80,000 feet, an unprotected human would lose consciousness in 3 to 5 seconds and die in less than 10. When NASA launched the first space shuttle mission in 1981, astronauts wore modified SR-71 pressure suits because NASA's own suits were not ready. Suit up began 90 minutes before flight. Physiological Support Division technicians assisted with every step, followed by pressure integrity checks, communications tests, and anti-fog system verification. Crews then pre-breathed 100% pure oxygen for 30 to 45 minutes to purge nitrogen from their bloodstreams, the same decompression sickness prevention protocol used by astronauts. The selection process to earn a seat in those suits was grueling. Pilots needed a minimum of 2,000 flight hours and clean records. Candidates underwent a week-long evaluation including a modified astronaut, physical, treadmill stress tests, brain scans, lung capacity tests, glucose tolerance screenings, sinus imaging, and a 1-hour psychiatric interview. Even social behavior was scrutinized. At least one candidate was rejected for getting drunk at the officers' club and criticizing the grooming standards of current SR-71 crews. From the cockpit, pilots saw the curvature of the Earth, a deep, inky darkness overhead, transitioning to the velvet black of space, and a bright blue band of atmosphere stretched across the horizon 400 miles distant. At 80,000 feet and above, the stars were visible in the daytime sky. The view was identical to what astronauts saw from orbit, and the experience was similarly profound. Ed Yielding recalled the sensation. You did not feel the speed so much when flying at Mach 3 because we were so high at well above 70,000 feet. The flight was always really smooth, no turbulence, and you just noticed that you got to your destinations in a hurry. It took less than 2 seconds per mile. Brian Schull, who would become the most famous SR-71 pilot of all, described it differently. The feeling of flying the Blackbird was unlike anything else in aviation. It was not fun, not exactly. It was intense, cerebral. You were operating at the edge of what was physically possible, in a machine that was unforgiving of mistakes, watching the planet slide by beneath you at speeds that seemed impossible. The sky above was black. The air so thin that if your suit failed, you had seconds to live, and yet there was a strange peace to it. A feeling that you had gone somewhere humans were never meant to go, and somehow returned. The program remained extraordinarily exclusive throughout its operational life. Fewer than 90 pilots ever qualified to fly the SR-71 operationally. Of those, only 19 accumulated 900 flight hours in the aircraft. Just 3 reached 1,000 hours. At any given time, roughly 9 to 10 operational crews were assigned to active flying duties. The rest served in training, planning, or administrative roles. More people have walked on the moon than flew 1,000 hours in the Blackbird. The SR-71 entered combat on March 21, 1968, when Major Jerome O'Malley and Captain Edward Payne flew the first operational mission over North Vietnam from Kadena Air Base in Okinawa. The locals had nicknamed the aircraft Habu, after a venomous pit viper native to the island that the Blackbird's sinuous shape resembled. The CIA's A-12 had preceded the SR-71 into combat, with the first Blackbird family combat sortie flown on May 31, 1967, during Operation Black Shield. But the SR-71 would serve far longer, far more widely, and would become the more famous aircraft of the two. Over Vietnam, sortie tempo escalated from 1 per week in 1968 to nearly 1 per day by 1972, sometimes 3 daily during peak operations like the linebacker bombing campaigns. Hanoi was described as the most heavily defended airspace on the planet, bristling with radar stations, SA-2 missile batteries, and MiG interceptors. SR-71 cameras achieved 6-inch resolution from 83,000 feet, sharp enough to read painted parking lot lines and identify individual vehicles, while side-looking radar and electronic intelligence sensors gathered data simultaneously. From operating altitude, the aircraft could survey 100,000 square miles per hour, covering the entire country of South Vietnam in less than 12 minutes. Approximately 800 surface-to-air missiles were fired at SR-71s during Vietnam operations alone. Pilots reported seeing missiles pass as close as 150 yards, their exhaust plumes visible through the cockpit windows, none connected. Not one. The 1973 Yom Kippur War produced some of the most dramatic SR-71 missions ever flown. On October 13, 1973, Lieutenant Colonel Jim Shelton and Lieutenant Colonel Gary Coleman departed Griffiths Air Force Base in New York on the first of a series of Middle East reconnaissance flights. The British government had refused landing permission at RAF Mildenhall, forcing round-trip flights requiring 6 aerial refueling from 16 Spain-based KC-135 tankers per mission. Shelton and Coleman's first sortie lasted 11 hours and 13 minutes, with more than 5 hours above Mach 3. The intelligence gathered was critical for providing President Nixon with real-time battlefield assessments. In Europe, the SR-71 operated from a permanent detachment at RAF Mildenhall, beginning in 1982. Between 1977 and 1988, 322 Baltic Express sorties were flown along the Soviet Baltic and Barents Sea coastlines, using side-looking cameras to photograph deep into Soviet territory without crossing borders. Swedish J. A 37 Viggen fighters regularly attempted intercepts, achieving missile lock in 51 of those sorties, though at combined closing speeds approaching Mach 5, those locks were fleeting. In April 1986, following the United States bombing of Libya, Major Brian Schul and Reconnaissance Systems Officer Major Walter Watson flew a post-strike damage assessment mission that became one of the most famous SR-71 sorties ever. When Watson detected SA-2 and SA-4 missile launches, Schul pushed the aircraft past its Mach 3.2 operating limit, reportedly reaching speeds in excess of Mach 3.5, covering a mile every 1.6 seconds. "The fastest we would ever fly," Schul later wrote. Brian Schul's path to that cockpit was itself extraordinary. Born February 8, 1948, he flew 212 combat missions in Vietnam before being shot down near the Cambodian border in April 1974. He crawled from the burning wreckage with burns over more than half his body, underwent 15 major surgeries, and was told he would never fly again. He returned to flying, progressed through A-7s and A-10s, and was selected for the SR-71 program in 1983, passing the astronaut physical with no waivers. His book Sled Driver and his famous speed check story became the most widely repeated SR-71 anecdotes in history. Schul passed away on May 20, 2023, at age 75, collapsing immediately after delivering his beloved SR-71 presentation at a gala in Reno, Nevada. Over the aircraft's operational career, thousands of missiles were reportedly fired at SR-71s. Not a single one ever hit. Soviet attempts to intercept the Blackbird were consistently futile. The MiG-25 Foxbat, developed specifically to counter high-speed American aircraft, could briefly reach Mach 2.8 at the cost of destroying its engines, but could neither match the SR-71's sustained speed nor reach its altitude. Soviet defector Viktor Belenko confirmed what Western intelligence suspected. American SR-71s taunted and toyed with the MiG-25s sent up to intercept them, scooting up to altitudes the Soviet planes could not reach, and circling leisurely above them or dashing off at speeds the Russians could not match. The single most harrowing SR-71 incident occurred on January 25, 1966, during a high-altitude test flight over the New Mexico desert. Test pilot Bill Weaver and flight test specialist Jim Zweyer were pushing the aircraft to its limits, evaluating high-speed handling characteristics at Mach 3.18 and 78,800 feet. The test card called for aggressive maneuvering at the edge of the performance envelope. Then the right engine suffered a catastrophic inlet, unstart. The carefully managed shock wave that fed the engine was expelled in an instant. Thrust on the right side dropped by 80%, while the left engine continued at full power. The resulting asymmetric force slammed the aircraft into a violent yaw and pitch up. Within 2 to 3 seconds, aerodynamic forces exceeded the aircraft's structural limits. The SR-71 disintegrated completely, the fuselage separating into multiple pieces at Mach 3. Weaver never reached his ejection seat. He never had the chance. His restraints sheared at the adjustment rollers, and he was physically ripped from the cockpit by the airstream tearing into the fragmenting fuselage. One moment he was strapped into his seat. The next he was tumbling through the atmosphere at 78,000 feet, watching pieces of the aircraft cartwheel away from him in the thin purple sky. His full pressure suit saved his life. It inflated automatically when exposed to the near vacuum conditions, preventing his blood from boiling and his lungs from rupturing. The suit's design prevented lethal tumbling by stabilizing his body position during the fall. Weaver lost consciousness almost immediately, his brain starved of oxygen despite the suit's emergency supply. He regained awareness during parachute descent, groggy and disoriented, his faceplate iced over from the extreme cold of the upper atmosphere. He could not see the ground approaching. He landed hard on a remote New Mexico plateau, stunned but alive. A rancher who had witnessed the distant flash of the aircraft breaking up drove out to investigate and found Weaver lying in the sagebrush. The nearest hospital was miles away. The rancher helped Weaver into his small helicopter and flew him to medical care. The helicopter's gauges redlined the entire way, a grim irony after surviving a Mach 3 breakup. Jim Zweyer was not as fortunate. His parachute deployed, but examination revealed he had suffered a fatal broken neck during the disintegration, likely killed instantly when the aircraft tore apart around him. He was the only fatality in the entire SR-71 operational program. Weaver was flying another Blackbird within 2 weeks. He went on to log hundreds of additional hours in the aircraft and became one of its most experienced test pilots. He passed away in 2021 at age 92, one of the last surviving original Blackbird pilots. The SR-71's defining records were set on that single extraordinary day in July 1976. Captain Eldon Joers and Major George Morgan established the world absolute speed record of 2,193 miles per hour, Mach 3.32. Hours earlier, Captain Robert Helt and Major Larry Elliott set the sustained altitude record of 85,069 feet. Both records earned the prestigious De la Volks Medal from the International Aeronautical Authority. Both still stand. 2 years earlier, on September 1st, 1974, Major James Sullivan and Major Noel Widderfield flew from New York to London in 1 hour, 54 minutes, and 56.4 seconds, averaging 1,807 miles per hour. The flight included one aerial refueling near Greenland. For comparison, the Concorde's best New York to London time was 2 hours 52 minutes. A Boeing 747 takes roughly 6 hours 15 minutes. That record also still stands. The aircraft's final flight was perhaps its most symbolic. On March 6, 1990, Lieutenant Colonel Ed Yalding and Lieutenant Colonel Joseph Vida flew from Palmdale, California, to Washington Dulles International Airport. They set 4 speed records in a single flight, all of which remain unbroken. Los Angeles to Washington in 64 minutes and 20 seconds, coast to coast in 67 minutes and 54 seconds. Kansas City to Washington in 25 minutes and 59 seconds. St. Louis to Cincinnati in 8 minutes and 32 seconds. The aircraft was delivered directly to the Smithsonian Institution, where it remains on display. 2 days later, Yalding and Vida flew coach on a commercial airliner back to California. A total of 32 SR-71s were manufactured. 29 operational variants, 2 two-seat trainers, and 1 hybrid trainer assembled from the forward fuselage of a static test article and the aft section of a crashed YF-12A, a combination the crews called the Bastard. Including the broader Blackbird family, 50 aircraft were produced. 12 SR-71s were lost during the program, everyone to mechanical failure or accident. Not a single Blackbird was ever lost to enemy action. The sole SR-71 program fatality was Jim Zweyer, killed in the January 1966 breakup. The retirement record holder logged 652 hours above Mach 3 across 900 total flights. Initial retirement came on January 26, 1990, driven by a combination of escalating costs and political maneuvering. The fleet cost roughly $200 to $300 million annually to operate, a figure that included the specialized JP-7 fuel produced at only one refinery, the dedicated KC-135Q tankers that could not be used for other aircraft, the unique maintenance facilities, and the highly trained ground crews. The aircraft required extraordinarily intensive maintenance, with comprehensive inspections mandated every 25 flight hours. The entire fleet consumed resources disproportionate to its size, but cost alone did not kill the Blackbird. Political factors played an equally significant role, and perhaps a more decisive one. Air Force Chief of Staff General Larry Welch, a former Strategic Air Command leader, wanted the SR-71's budget redirected to B-2 bomber development. He testified before Congress that a single SR-71's annual operating cost could fund a wing of 15 to 20 15E fighter bombers. Ben Rich, Kelly Johnson's successor at Skunk Works, called this claim bogus and argued that the comparison was misleading. Secretary of Defense Dick Cheney personally supported ending the program. In an era of tight budgets and competing priorities, the Blackbird lost the bureaucratic battle. The aircraft that had never been shot down was retired by a memo. Congress briefly reactivated 3 SR-71s in 1995, initially allocating $100 million before budget cuts, reduced the funding to $72.5 million, responding to concerns about intelligence gaps. But the reprieve was short-lived. The Air Force leadership that had wanted the program dead continued to resist funding it. The reactivated aircraft flew limited missions before being permanently retired in 1998. NASA operated the last 2 airworthy SR-71s for high-speed research until the final flight on October 9, 1999, during an Edwards Air Force Base open house air show. Thousands of spectators watched as the black aircraft made its last takeoff, climbed into the California sky one final time, and disappeared to the east. When it landed, an era ended. The fastest air-breathing manned aircraft ever built would never fly again. 20 surviving SR-71s are displayed across the United States and at one location abroad, silent monuments to an age of engineering audacity. The most historically significant sits in the position of honor at the Smithsonian National Air and Space Museum's Udvar-Hazy Center near Washington. Aircraft 617972 the transatlantic record holder and the retirement record holder, with more than 2,800 flight hours and 652 hours above Mach 3. The National Museum of the United States Air Force at Wright-Patterson Air Force Base holds aircraft 617976, which flew the first operational SR-71 mission and logged 257 operational sorties over its career. The sole SR-71 outside American borders resides at the Imperial War Museum, Duxford, in England, a tribute to the years of operations from RAF Mildenhall. Others can be found at the Pima Air Museum in Tucson, the Air Zoo in Kalamazoo, the Museum of Aviation at Robbins Air Force Base, the Strategic Air and Space Museum near Ashland, Nebraska, NASA's Armstrong Flight Research Center at Edwards, and on the flight line at Beale Air Force Base itself, among other locations. Visitors can walk up to these aircraft, touch their titanium skins, and try to imagine what it was like to fly at the edge of space at 3 times the speed of sound. The question of why no publicly known aircraft has replaced the SR-71 has no single answer, and the answers that exist are frustrating to those who remember what the aircraft could do. Reconnaissance satellites eventually matured enough to cover most strategic intelligence needs without the political risks of airspace violations. Imaging resolution improved. Coverage expanded. The National Reconnaissance Office could task satellites to photograph almost anywhere on Earth. But satellites have fundamental limitations that no amount of technology can overcome. They orbit in predictable paths. Adversaries know precisely when American reconnaissance satellites will pass overhead and can time their activities accordingly. Mobile missile launchers can move, aircraft can be hangared, troops can disperse. Repositioning a satellite over an unexpected crisis zone can take 24 hours or longer. The SR-71 could be deployed anywhere on Earth within hours of a presidential order. The gap became painfully apparent during the 1991 Gulf War, when General Norman Schwarzkopf was dismayed to find SR-71 reconnaissance unavailable for hunting mobile Scud missile launchers in the Iraqi desert. The Scuds moved constantly, hiding by day and launching by night. Satellites could photograph their last known positions, but the launchers would be gone by the time the images were analyzed. An SR-71 could have covered the Scud boxes repeatedly throughout the day, providing near real-time intelligence on launcher movements. The aircraft's absence was felt precisely when its speed and flexibility were most needed. Schwarzkopf made his frustration known to anyone who would listen. In 2013, Lockheed Martin's Skunk Works publicly proposed the SR-72, a Mach 6 hypersonic successor that would nearly double the Blackbird's speed using a turbine-based combined cycle engine that would function as a turbofan at low speeds and transition to a scramjet at hypersonic velocities. The company projected a prototype flight by 2025 and potential operational service in the early 2030s. As of early 2026, no confirmed flight tests of the SR-72 have occurred. Reports indicate the program has accumulated significant cost overruns, and the technical challenges of sustained hypersonic flight remain formidable. The Air Force chose instead to develop stealth, unmanned systems that trade the Blackbird's speed for invisibility and endurance, aircraft that can loiter for extended periods without the physiological limitations of human pilots. The Northrop Grumman RQ-180 flying wing drone is believed to represent the closest practical replacement for the SR-71's penetrating reconnaissance mission, though its existence has never been officially acknowledged. It can go where satellites cannot reach on short notice, but it cannot outrun what the Blackbird could outrun. Different era, different priorities, different trade-offs. The Blackbird's design pioneered concepts that influenced everything that followed. Its canted vertical stabilizers, radar-absorbing coatings, and cross-section reducing shapes were direct ancestors of the stealth technology later refined in the F-117, B-2, F-22, and F-35. Its pressure suits evolved into NASA Space Shuttle crew escape equipment. Its engine inlet technology informed decades of supersonic propulsion research. The SR-71 Blackbird was conceived in desperation after a diplomatic catastrophe, built from materials secretly sourced from the very nation it was designed to spy on, powered by engines that existed nowhere else in aviation, and flown by fewer pilots than have walked on the moon. Over a quarter century of operations, it was targeted by missiles from multiple nations and never hit. It still holds speed and altitude records set in 1976 that no publicly known aircraft has approached in 5 decades. Kelly Johnson's team took requirements that appeared physically impossible, sustained flight at 3 times the speed of sound, for hours at a time, at the edge of space, and built an answer using tools and materials that did not exist when they started. They invented the metal fabrication techniques, the fuel, the ignition chemistry, the engine cycle, the thermal management systems, and the pressure suits. They solved problems that had no precedent. The aircraft that leaked fuel on the ground transformed into an airtight vessel in the sky. The titanium that shattered in workers' hands became the strongest airframe ever built. The engines that operated as turbojets at takeoff became ramjets at cruise. The pilots who wore spacesuits to go to work looked down upon a curved Earth from an altitude where the sky turned black. 61 years after Bob Gilliland's first flight, the SR-71 remains what it has always been, the fastest air-breathing manned aircraft ever to fly, an engineering achievement that has never been equaled, a machine that flew so fast its titanium skin glowed red and that still holds the records to prove it.